Many NLP applications rely on adapting one large-scale, pre-trained model for multiple downstream tasks. As models grow increasingly large, with GPT-3 and GPT-4 possessing 175 billion and 1.76 trillion parameters respectively, full fine-tuning becomes prohibitively expensive. Even when loading with 16-bit floating point, GPT-3 takes 326 gigabytes of VRAM to run for inference. In 2021, researchers at Microsoft unveiled LoRA, low-rank adaptation of large language models. The paper addressed the prohibitively expensive cost of fine-tuning LLMs for downstream applications. This approach freezes the pre-trained weights and injects trainable rank decomposition matrices into each layer of the transformer architecture. This significantly reduces the number of trainable parameters for downstream tasks, yet still achieves state-of-the-art. Despite these improvements, it still requires significant compute and GPU memory to fine-tune these large models. Here, we present QLoRA, efficient fine-tuning of quantized LLMs. QLoRA significantly reduces the memory usage enough to fine-tune a 65 billion parameter model on a single 48 gigabyte GPU, while preserving full 16-bit task performance. This paper demonstrates that it is possible to achieve state-of-the-art fine-tuning on a small, high-quality dataset, even when using smaller models than previous state-of-the-art. This development is extremely valuable for increased access and reduced resource requirements for fine-tuned models. QLoRA relies on three separate innovations to save memory without reducing performance. They are 4-bit normal float quantization, double quantization, and paged optimizers. QLoRA introduces a novel data type called 4-bit normal float, or NF4, which is specifically tailored for normally distributed weights commonly found in neural networks. NF4 works by quantizing weights to a 4-bit format while ensuring that the quantization process is information theoretically optimal. This means that each quantization bin is equally likely to be used, reducing the information loss typical of traditional quantization methods. The resulting 4-bit representation maintains high fidelity to the original data distribution, thus preserving the model's performance even with significantly reduced memory footprint. Double quantization is a 2-layer quantization strategy implemented by QLoRA to further decrease the memory required for model parameters. The first layer of quantization reduces the data to the NF4 coarser representation, and the second layer quantizes the quantization constants themselves down to 8-bit, which are normally stored at a higher 32-bit precision. This method compresses the model further by reducing the average memory required per parameter by about 0.4 bits. To handle the memory spikes that occur during backpropagation of gradients, particularly with large mini-batch sizes or long sequence lengths, QLoRA utilizes paged optimizers. This technique leverages the NVIDIA Unified Memory System, which automatically manages memory transfers between CPU and GPU. When the GPU's memory capacity is exceeded during intensive computations, paged optimizers allow portions of the data to be paged out to the system's main memory, then paged back in when needed. This dynamic memory management prevents out-of-memory errors during training, which is a critical feature to allow even very large language models to be trained on hardware with limited GPU memory. The results from the QLoRA paper are impressive, demonstrating the effectiveness of the proposed method. QLoRA successfully fine-tuned a 65 billion parameter model on a single 48 gigabyte GPU, achieving near state-of-the-art results on multiple benchmarks. The Guanaco model family, developed with QLoRA, performed exceptionally well. Guanaco 65B achieved 99.3% of the performance of ChatGPT on the Vicuna benchmark. QLoRA represents a significant advancement in LLM fine-tuning. By innovatively reducing memory requirements, QLoRA enables the fine-tuning of massive models on modest hardware, democratizing access to cutting-edge AI resources and technologies. The success of the Guanaco model illustrates the potential of QLoRA to maintain high performance, making it a valuable tool for researchers and practitioners working with AI on limited resources. This approach not only optimizes resource use, but also opens new possibilities for AI applications in resource-constrained environments.